Hello, everyone, and welcome to this webinar about Cloud HPC and, in particular, the monitoring of FDS analysis for fire safety simulations. This is Ruggero Poletto from CFD FEA Service, and we're gonna spend the next half an hour together discovering how we can set up FDS analysis in order to completely monitor our simulations. Before we actually start with the presentation, a couple of hints. This webinar is going to be interactive between me and yourself who is listening. So I suggest you at every time to take advantage of the chat you can find next to the video and interact with me. I'll keep an eye on the chat I have over here so I can reply to your questions at any time during the presentation. A small presentation of the company. The name of the company is CFD FEA Service. It's been founded in 2018. We are settled in North Italy, close to the city of Verona. Our main business area are basically three at the moment. We are obviously involved in software development, as in particular, as far as engineering applications are concerned. We provide a cloud HPC system that we're going to see later today, which allows people to execute simulations using remote hardware resources. And obviously, we also involved into the consulting and engineering design and activities in general, uh, in civil application and also in mechanical engineering applications. Today, we are going to talk about FDS, which is a CFD software dedicated to fire simulation. FDS is the acronyms for Fire Dynamic Simulator. And in particular, we are going to focus on the ASET and RSET calculations. ASET stands for Available Safety Escape Time, and RSET is Required Safety Escape Time. So every time we are dealing with a fire simulation, a fire safety engineering analysis, we have somehow to predict what is our available time, the time which we can allow a safe condition in our building, in our car park, in our rooms, for the occupants to not just to be alive, but to be ready to escape and to find a way out in the case of fire. This ASET analysis is usually made with a CFD analysis, and from the CFD analysis, we have to monitor few parameters in order to actually determine how long we can maintain safe conditions inside of our building. And then there is the RSET analysis, which is the required safe escape time. So the time required by the people, by the occupants of our compartment, of our room, to actually leave the building. Okay, so this is actually a sum of two or three of few times. There is the detection time, the alarm time, recognition time, response time, movement time, which is actually the escape phase, and then there is a safety margin. Usually, to do this, there are several software, obviously, but they are agent-based or flow-based. So they simulate the occupants as agents or as a sort of fluid which has to pass through the safety exit of our building. Today, we are actually only focusing on the ASET and how can we determine how long is our available safe escape time. Okay, what is the threshold we are monitoring, and the point when we said, okay, our available, we cannot guarantee safe condition in our building anymore. Even if we have an extraction, a smoke extraction system, even if we have a system to control the smoke, but still, okay, we have to determine what is our available safety escape time. So in here comes the ISO 13571 version 2012, which tell us several things. And the easiest, let's say, in the easiest way we can read it, it tells us to monitor four parameters. One is the gas temperature, so the temperature of the air inside of our building, or at least in the room, in the compartment where the fire scenario is going to be applied by our CFD analysis. The second parameter is the smoke visibility. So how far I can see inside my room because the smoke is propagating inside this room. And so I have to monitor how far away I can actually see around. Then there is this FED, which is, since I am an occupant of this room, I am inhalating some smoke and some toxic particles because of the presence of the smoke and on the fire scenario in this room, and how long I can resist this inhalation of criticals and particles, let's say, from the room where I am right at the moment. And then there is radiation. Radiation is somehow connected to the heat transfer that the smoke is radiating everywhere in the room. And it depends on the temperature of the smoke mainly, and the temperature of the fire as well. And this has to be monitored in order to remain below a certain threshold. Well, in our simulation, basically, we have to monitor all these four parameters and detect the one which reaches a sort of threshold, the first to reach this threshold among these four parameters. Everyone has his own threshold, and we're going to see how to monitor that. So let's have a look quickly at two models, because gas temperature, well, that's easy to calculate. It's just a temperature at a certain level. And for radiation, well, that is also a physical calculation. We just calculate how much heat is radiated by the fire. But the other two parameters, the smoke visibility and the FAD, they require some modeling. Okay, so let's starting from the smoke obscuration model that's already implemented in FDS, but it's worth a while knowing that basically we can determine the L, which is the smoke distance at which we can actually see, which we can actually detect an object, which is equals to given by this formula, in which we have a mass specific extinction coefficient, which for FDS is 8,700. And then we have the density of the air, which depends on the temperature, but let's say the ambient temperature is 1.2 kilograms per cube meter. This model is already implemented in FDS, okay? And we can modify the coefficients we have in FDS, obviously, if we have particular like reflecting body, light reflecting body, or we have an opaque one. Okay, so we can modify these parameters if we want, but in general in FDS we have this parameter working for non-light refracting bodies. Okay, so that's worth a while remembering when applying this smoke view parameter. And then there is the FED. FED is the ratio of the exposure dose to efficient and toxic substances. So since we are in a place in which there is smoke and uh, gases like CO or other toxic gases are produced, we are breathing these substances, and there is a level to which every human can resist up to that level and be, let's say, still reactive and respondent. Once we get beyond this level, well, we won't be able to be reactive and respondent to this, to any external situation. So there are two models that can be used. One is based on asphyxiant gas model, and the second one is the irritant gas model. We are just going to focus on this second model because it is the one which is actually implemented in FDS. So the idea of this model is that we take all the irritant gases and we do a ratio between the actual gas concentration and the gas concentration that would take an F and would compromise occupants' ability to take effective action. Okay, so we take this phi HCl and F HCl. This is a ratio between the actual concentration and the maximum concentration that an occupant can resist. And we sum up all the concentrations for all the gases, all the irritant gases produced by our fire scenarios, and all together we obtain the FEC. This is actually the FEC. And thanks to this, okay, we can get a parameter which somehow sum up all the contributions uh, to the irritation of the occupants given by several gases. Well, the sum of all these contributions gives us the total FEC that is subjected to the occupant. Well, according to the ISO 13571, the limits we need to monitor in our CFD analysis is for the gas temperature is 60 degrees Celsius. So once we get beyond this threshold, well, our available safe escape time is no more guaranteed according to this first parameter. For the smoke visibility, we have 10 meters. For the FED, we have 0.1. This is a sort of percentage. And for the radiation, we had 2.5 kilowatts per square meter. So these are the four parameters we have to monitor in our simulation in order to actually understand if we still can guarantee safe escape conditions or we cannot guarantee that anymore. So coming from this is a little bit simplified, let's say, because actually these gas temperature conditions are actually double because they are valid for the occupants and there is a separate condition valid for the fire brigades that come in help, and the same is also valid for the radiation. But let's just take the basic thresholds for our case. And I forgot to mention that this threshold has to be measured at 1.8 meters from the floor. So we know the location where we had to measure these thresholds and the thresholds for all the four variables we're going to measure. Well, having a look at FDS and what are the monitor possibilities that FDS give us, well, we have what we can call slices. Basically, we take our CFD analysis and we take a slice of our domain. And on this slice, we can monitor a certain quantity like temperature. Okay, so thanks to a slice like this one, we can monitor temperature and detect if the temperature goes beyond the 60 degrees Celsius we saw earlier. So this is quite a good example of how we can implement something in FDS to monitor the temperature. But this is not the only type or possibility of monitoring we have in FDS. We also have boundary conditions. Like in here, thanks to this command, we can monitor on a boundaries, on a solid walls, we can monitor the temperature of these walls. Well, for the radiative heat transfer, this is very important because radiation is actually a quantity that exists once we hit a solid surface. So the best way to monitor that is to actually monitor the radiation, the radiative heat transfer on the boundaries of the solid walls of our analysis. And then we have isosurfaces. Basically, these allows us to detect, like in here, an isosurface, so a volume, uh, a surface on which we have a constant temperature of 50 degrees Celsius, 200 and 500 degrees Celsius in this example. And it allows us to understand where we are getting above our thresholds, our monitoring thresholds. Finally, we have another very specific way to monitor quantities in our analysis, and this is called the device. Well, device is basically a point in our domain defined by three coordinates, x, y, and z. And in these three coordinates, we can monitor a specific quantity like temperature. Thanks to this, it is possible to actually have a it's like a probe in which we are monitoring temperature, we can monitor smoke visibility, and as we're going to see later, even if it is very localized, for the Fed, we are going to use these devices because they are able to produce calculate the Fed in a specific location. So we are gonna add some devices all over our domain in order to capture the Fed. So I said several times we can monitor quantities thanks to slices, boundary devices. But what are the quantities? What are the quantities we can actually measure in FDS? Well, there are quite a few of them. This is part of the list. In this first part of the list, we can already see that we have a boundary, a quantity specific for a radiative heat flux, which is what actually has been specified by the ISO 13579 earlier. And this is measured in kilowatts per square meter, so exactly the unit we needed. And it can be measured, you can see, on the boundaries and on devices. Okay, so slices cannot measure this particular quantity. That's why we said earlier that we need boundaries to monitor, solid boundaries to monitor this quantity. These are some more quantities, and here we are. We have visibility, which is given in meters, and this can be measured by devices, isosurfaces, and slices. Okay, so we're gonna use slices to monitor visibility. We have Fed, okay, we saw it earlier, and we can monitor it just by devices. So we have to add a few devices to our simulations in order to monitor the Fed. And eventually we had temperature, which gives us the gas temperature in Celsius degrees, and this can be monitored by slice. So we're going to use slice to monitor this. So as we said earlier, so we're going to use slice for the visibility, device for the Fed, slice for the temperature, and if I go back, we're going to use boundary for the radiative heat flux. So there is also actually an alternative way to measure the Fed. This is implicit in the smoke view. I don't like that a lot, but we are going to see that as well. So basically, if we add three slices, and in each of these slices, we measure the volume fracture of carbon dioxide, carbon monoxide, oxygen. Well, in that case, smoke view is actually calculating the Fed and is going to provide us the Fed as a slice as well at the very same location where we are taking it. Here it means this PBZ equals 1.8 means 1.8 meters from the ground. So this is an alternative way, an indirect way to measure the Fed, but I still prefer to use devices as we're going to see later. Another thing we are discovering today is the possibility to execute this simulation on the cloud. So since FDS is highly demanding in terms of hardware resources, what we are going to do is setting up the simulation on our computer uploading that on the cloud and executing it using remote hardware resources. The main advantages in doing that is that we can speed up our analysis. We can rely on good hardware and always updated hardware. And also, we don't have to install newer version of FDS because on the cluster, everything is maintained by ourselves. Another thing which is important, we're going to see later, is how to set up the thresholds for all the quantities we are going to measure. We're going to see this slide later. First, before actually moving on, I wanted to show you the FDS file I have prepared for this case, and we can see that together how we can I have implemented the thresholds in the FDS file. So this is a simple geometry, is a corridor. We have a certain heat transfer. I already prepared the mesh. We have a total simulation time. I'm not going through everything I did for this analysis, like obstruction. This is the geometry settings. Uh, it would take like not a webinar, it would take a complete course, a training course, in order to know exactly what is present over here. But we are going to have a look at the tail look of these three lines over here. Well, in here we are. I am monitoring three of the four parameters mentioning in the ISO 13571. So the first one is something I always suggest to monitor is the velocity, and place it as a vector so we can have a vector plot of the velocity. The second quantity is temperature. So this is actually the first threshold we have to monitor given by the ISO regulation. The second one is the visibility, and again, another quantity to measure for the ISO. And the third one, you can see this is under slide, this is on the boundaries, is the radiative heat flux. All right. And then we have the possibility, the last parameter we have to monitor is the FAD. As I said before, for the FAD, we have two possibilities to analyze that. One is adding these three slices, carbon dioxide, carbon monoxide, and oxygen, and automatically SmokeView is going to calculate the FAD. They have to be at the same location, so it's 1.8 meters from the ground. The second way to calculate the FAD is to add, if you see, several devices. Any of these devices has a slightly different location. You see, the location is 0, 0, 1.8 meters from ground, 0, 0.5, 1.8, 0, 1, 1.8, and they are all monitoring the FAD. So thanks to this, we can see the FAD in SmokeView. But thanks to this, we are going to produce a CSV file we can open using Excel. And at all these locations, we are monitoring the FAD. And we can compare it with the ISO regulation. So, well, this is the file. We go to the cloud. This is the cloud platform where we're going to execute the analysis. Well, this to set up an analysis, well, that's quite simple. We had to go under the storage. We just upload the file. So I just press the plus button. I browse in here. I just go to download, and I prepare the file inside this folder. So I just upload the file over here. I press save, and automatically I can upload the file onto the cloud platform. And here now in my storage, I can see the FDS file I have just uploaded. Now I can go to the simulation page. I can press plus. And in here, I select the configuration of the machine I want to use. For this particular case, I want to use 8 virtual CPU. As CPU type, I'm going to use high mem, which allows us to give a huge amount of RAM per CPU. We execute the FDS file, and in here we have all the scripts available, among which we have FDS version 6.8.0. We press save, and we are submitting, thanks to this, the job on the cloud. This is the simulation we are launching. I can enter the details of this analysis. You see the status is still pending. It takes about 3 minutes to actually start the analysis, not from the pending status, which is moved to running straight away. It takes, you see now it's running. And what happens is that while the simulation is running, the system is actually generating a virtual machine in which we are going to execute the simulation, in which we are going to upload FDS 6.8, in which we are going to upload the FDS file we put in the storage, and we are submitting the job on the cluster. Well, the generation of this virtual machine takes a couple of minutes, so we're going to wait for that together for the simulation to start. I just resumed the simulation, the presentation a little bit, just to show you what we have to do, because in Smoke View, once we upload all the slices, like the visibility, we are now going to give you a range of values as prescribed by the ISO regulation, but the range of values we're going to see is the one is between the minimum and the maximum visibility in our domain. So usually most of the times it goes from 0 to whatever is the maximum value of the visibility in our domain. In Smoke View, we have then to change the settings in order to restrict the range of acceptable values only to those prescribed by the ISO regulation. To do that, we load the slices, and then we're going to go to settings. We expand the slice section, and we go into the bound or truncate data. In here, we can select the variables we want to monitor. We expand the bound data, and then we modify the minimum and maximum range which are acceptable according to the ISO value. We had to do this for the slices and also for the boundaries. We do it for the boundaries because the radiative heat transfer is not present in the boundary, but it's actually it's not present in the slices, but it is actually present in the boundaries. So we move on and we go again to our cloud platform. You see now this simulation is actually starting. If I just refresh the page, I can see this is the remote desktop. This is a remote desktop to the machine where the FDS analysis is actually running. And over here, I can actually see the usual FDS log as I'm used to see in most of the FDS run I perform also on my local computer. Here in the desktop, we have a button which is Smoke View. We just double click that. And this is going to automatically open Smoke View. This is Smoke View, as we can see earlier. If I zoom in a little bit, now sure you can see all these green dots. These are all the devices we are using to monitor the FED. So these are those devices I mentioned before. And now, before actually executing the simulation or actually having a look at the results, as I said before, we are going to go to settings, expand bound data. And so we set our minimum thresholds, as we said earlier. So we want the temperature between 20 degrees and we said 60 degrees. For the visibility, the minimum is going from 0 to 10 meters, not to 30. So we just check everything is all right. For the FED, minimum value is 0, and maximum value is 0.1. All right, so this is okay. Then we have to modify under boundary bound data, the radiation, which has to go from 0, so we just cancel all of this, to, if I remember correctly, is 2.5 kilowatts per square meter. We save settings, we close everything. Sorry. What is nice is that we can save this configurations file into save settings into this case, into a .ini file. So what is nice is that if I now open next time the smoke view, I will automatically have all these settings which are saved in this file in particular, the .ini. All right, simulation is proceeding. We want to load then a slice. Why not? Let's start with the temperature. So we have this temperature at 0.8. As you can see, okay, I'll just stop a little bit. All right. As you can see, the dark, the red part of the slice is where the temperature is above our 60 degrees thresholds. So in this area, we cannot guarantee a safe escape time already after 10 seconds. In the green and the blue parts, well, everything works smoothly because we can be at about 20 or 30 degrees Celsius. So that's one of the things we can see, we have to monitor. Another one regards the smoke visibility. So you can see smoke visibility also at the very last time step, which is about 13 seconds right now, is higher than 10 meters. So for the smoke visibility, there's no really a limitation, okay, in this case. We're not producing that much smoke. And this can be seen also by uploading the smoke density, okay. If you'll upload that, we cannot see any smoke, even if actually some smoke is actually produced. Then we have under boundary. Actually, we unload everything before. And under the boundary, I wanted to show you the radiative heat flux. So once again, we go to the last time step. And what we can see is that everything is blue, or we have some green area, let's say close to the fire. But you see in the green area is 1 kilowatts per square meter. So still it's an acceptable value. But again, the red one is the one we don't want. Obviously close to the fire, and let's say close to the fire in general. Then we also have the possibility, so we unload everything, to open the FED. I just open it once again. You see, FED is actually not loading in this moment. Sometimes it can be problematic. What I suggest for the FED is to actually use the devices. That's why we place them. So you enter your case. Usually there is a CSV file, which is this one. Is underscore devc.csv. This means devices.csv file. We can open this file. In this case, I don't have Excel installed on the remote cluster, but you can see over here that step by step, all the devices are actually monitoring the FED. Since there is a little amount of smoke, we have some devices getting one 10 to minus 5, which is 0.00001 in terms of FED. The limit is actually 0.1. Okay, so we are about 3 or 4 orders of magnitude below the limit. So it is still acceptable at this stage, at this moment, to have this level of FED. But it depends on how the simulation advances, how what's going to happen for this analysis. So yeah, as you can see in the cloud, the simulation is moving on. We are already at 20 seconds, and just for the clarification, we can open again the temperature, and you can see probably in this case is the temperature is the biggest limit. As you can see, already at 20, after 20 seconds, we reached almost all the lower level of our corridor to be out of the 60 degrees range specified by the ISO regulation. So in this particular case, temperature seems to be the more strict parameter to look at, but this can depends on the configuration, on the geometry, on the fire scenarios we're simulating. It can be different in other cases. So now, since the example is completed, we can stop the running analysis. There is a stop button in here, and we just press stop. The system takes care of it and is going to stop the analysis. And once it's completely stopped, under the storage, I have now this folder, and under the storage inside of this folder, I will be able to download the results of my simulation. And consequently, I will be able to post-process also the results in my local computer. So I resume the presentation. Well, before actually finishing, I wanted to let you know about the prices of the Cloud HPC platform, which has been used in order to execute this small analysis. Well, the prices ranges from 0.04 euro per virtual CPU hours to 0.12 euros per virtual CPU hours. So this is the lowest rate and this is the highest one. It depends a little bit on the configuration of your analysis and how much RAM you're going to use. But the good thing is that there are no upfront payments by default. Basically, everything is based on the consumption you made to the platform. So you are free to use the simulations platform. And at the end of the month, you're going to be a transaction is made depending on how many CPU hours you have used on the platform. And it is possible to get some discounts from these prices by making upfront payments or by having sustained usage, so a huge amount of CPU hours used every month. And for example, the progressive discount is automatically applied every month, and it depends on how much you spent in the platform every month. So up to 400, you don't get a discount. From 400 to 1000, you get 10% discount, and so on, up to a 30% discount if you have a very sustained use of the platform. With this, I have finished my presentation of the Cloud HPC platform and on the ISO regulation, how we can monitor the thresholds imposed by the ISO regulation using FDS. I don't see questions in the chat, but so I can invite you to email us. I provide two email. One is specific of the company. One is dedicated to the Cloud HPC platform we saw together. And obviously, I also invite you to register to the platform, as the registration is free of charge and gives you 300 virtual CPU hours to use on the platform to test it for your simulation and also to validate, let's say, your results with the ISO regulation. With this, the webinar is over. I thank you all for taking part to it, and I invite you to keep an eye on our social media for future updates and future webinars. Thanks to everyone for taking part to this webinar, and see you next time. Bye.